Today in this video, I am going to explain the concept of differentiability of a function at a point. So let's start. A function fx is said to be differentiable at a point a function fx is said to be differentiable at a point x is equal to a if limit h tends to 0 f a minus h minus fa divided by minus h is equal to limit h tends to 0 f a plus h minus fa upon h. A function fx is said to be differentiable at a point x is equal to a if limit h tends to 0 fa minus h minus fa upon minus h is equal to limit h tends to 0 fa plus h minus fa upon h. This limit is called left hand differential. And this limit is called right hand differential. So in other words, we can say that a function fx is said to be differentiable at x is equal to a if its left hand differential and right hand differential at the point are equal. Geometrically, if we talk about differentiability of a function, then a function is said to be differentiable at a point if to the curve of the function at a point, if a tangent can be drawn, then the function is said to be differentiable at that point. For example, suppose curve of the function y is equal to fx is this. So suppose this point is x is equal to c. X is equal to c is this point. So at this point, if a tangent can be drawn, at this point, the function fx is said to be differentiable at this point, at x is equal to c. So for better understanding, let us take an example to examine the differentiability of a function at a given point. So suppose the example is examine the differentiability of fx at x is equal to 2 if fx is equal to 1 plus x when x is less than or equal to 2 and fx is equal to 5 minus x when x is greater than 2. So first we will find out the left hand differential, that is limit h tends to 0 f 2 minus h minus f2 divided by minus h. So that is equal to limit h tends to 0. Now 2 minus h is considered to be less than 2 when x is less than 2. The function has the value 1 plus x. So in 1 plus x expression, we have to replace x by 2 minus h, that is f 2 minus h. 1 minus 2 minus h minus f2. Now f2 is the functional value of the function, so we see where x is exactly equal to 2, what is the value of function. So we see in these two conditions where is the sign of equality. The sign of inequality is with this less than sign. So when x is equal to 2, the function's expression is still 1 plus x. So in this expression we have to substitute x is equal to 2 directly. So we will have 1 plus 2, 1 plus 2, that is the functional value at x is equal to 2, divided by minus h. So let us simplify. Limit h tends to 0, 1 plus 2 minus h minus 3 upon minus h. So see, 1 plus 2, 3, positive 3 and negative 3 will cancel each other, and we have limit h tends to 0, minus h upon minus h. Minus h is cancelled by minus h from numerator and denominator, and we have only limit h tends to 0, 1. Applying the limit, we have 1 because there is no h. So this is the value of left hand differential. Let it be equation number 1. Now let us see what is the value of right hand differential, that is limit h tends to 0, f 2 plus h minus f2 divided by h. That is equal to limit h tends to 0. Now we have to find out f2 plus h. f2 plus h. 2 plus h is considered to be greater than 2 symbolically. So in our function we have to observe the condition x is greater than 2. For that function fx is equal to 5 minus x. So in this expression, that is 5 minus x, we have to substitute, we have to replace x by 2 plus h. So 5 minus 5 minus x. X is replaced by 2 plus h, that is f2 plus h, minus f2. f2 is already we have calculated in the previous section, that is in the case of left hand differential, that is 3. So we write 3 f2 upon h. Now limit h tends to 0. If we open the bracket, we have 5 minus 2 minus h minus 3 upon h. So here limit h tends to 0. Here minus 2 and minus 3, negative 5 and positive 5 will cancel each other, and we have only minus h in the numerator and plus h in denominator. H is cancelled by h, and we have limit h tends to 0 minus 1. Now applying the limit, we have minus 1 because there is no h, that is 1. Let it be equation number 2. So as we observed, the value of left hand differential is 1 from equation number 1, and from equation number 2 the value of right hand differential is minus 1. So the value of left hand differential is not equal to the value of right hand differential. So we may say that from equation 1 and 2, limit h tends to 0, f2 minus h minus f2 upon minus h, that is left hand differential, is not equal to limit h tends to 0, f2 plus h minus f2 upon h, that is right hand differential. So fx is not differentiable at x is equal to 2 So this is the way to check or examine the differentiability of a given function at a given point.